Now we'll look at a second possible controller design. For this controller, I'm going to stay with complex conjugate zeros in my controller, and this represents, again, just a second design choice we could make of an infinite number of complex conjugate zeros we could choose for the controller, or real zeros that we could choose instead. So for this design, we're going to stay with the same desired closed loop pole locations at negative 1.15 plus or minus 2.11j. That will be the same between the two controller designs. But what I'm going to vary in this one are the zeros for the controller. So now for the real part, I'm going to let a equal 6 for my z1 and z2, placing the zeros with a real part at negative 6. So this one will be further to the left in the left half plane than our first design choice. But because we're adding two zeros to the system, it's not going to be quite as obvious what the results are going to be when we actually go through the simulation. So I'm going to let a equal 6. So this step looks exactly the same here. I'm putting in 6 for my real part, so I still have to find what is the imaginary component. So angles are still defined the same way. It's the arctangent, the 4-quadrant arctangent of the imaginary parts over the real parts. And now I need to solve for the b that's going to satisfy this equation. Just like the first design, analytically this is not going to be easy to do, so I'm going to do this numerically. So using my fzero solver here in line 16 now for design number 2, I have here my desired pole location. Again, I'm using the negative 2.11 for everything in this calculation. It still has to add up to negative 7 because that will, again, guarantee my desired pole will be on the root locus. But now for that z1 and z2, I have the real part of 6, and I need to find the imaginary part, the b, which, because it's imaginary, I multiply that by the 1j. So I can solve this now for my value of b that makes this true. In this one, I'm making my initial guess equal to the real part of 6, and we see that it does find that my 0 should be located at 12.1. I'm going to round to just 3 digits for this. I could make it 12.15, maybe get a little bit more precision, but I'll just stick with 3 digits and it will be close enough because there's going to be a bunch of other things that throw off the exact results anyway. So I'm going to proceed with 12.1 being the coefficient for my imaginary part. So this means that z1 and z2 at 6 plus or minus 12.1j will guarantee that my desired pole is going to appear on the root locus. So using this z1 and z2, I can make my root locus transfer function, that g prime, by putting in the values for z1, z2, and then distributing and multiplying everything through so that I'm going to be able to put this expression into MATLAB, into a transfer function, and then into my root locus. When I multiply everything through, I get a different g prime than I got for design number 1, which should be expected because z1 and z2 are different. I'll get s squared plus 12s plus 182 over s squared plus 2s for my root locus transfer function. So first step, like before, I have my z1 and z2. I need to find my gain that's going to guarantee that I have my desired closed loop poles. So I need to make the root locus, but now for this value of g prime. So going into that same code I used for design number 1, I'm going to up here just change it to design number 2. So now I'm going to make this transfer function for my root locus, and that's what I had on the slide before. And that's what I want to find the root locus of. So let's first look at the root locus. Running the code, I get this different looking root locus than I had for design 1. And again, I need to find on here where are my desired poles, or at least close to them. So if I start shifting around where this is, I'm going to say that this point is the closest I can get. So it has my closed loop pole at negative 1.15 plus minus 2.04j or I here. And that's, I think, as close as we're really going to get. I'll keep the real part as close as possible. So if I used a little bit higher gain or a little bit lower gain, it's not a big deal. It's not going to change it too much. And with some of the rounding, like using only 3 digits for that b value, I'm not going to get exactly the desired pole location, but I mean, I'm pretty close here. So this being the closest pole, this is saying use a gain of 0.031. Now I use the gain I just found, the 0.031, multiplied out by the zeros that I found before, the 6 plus or minus 12.1j. And I'm going to expand this out so that I get those 3 gains, which is how I'm going to implement the controller in Simulink. So if I multiply through, this tells me that my proportional gain should be 0.372, the constant part on the right-hand side, the derivative gain 0.031, that's times the s term, and the integral gain 5.65, that's the part that is being divided by s, so that's going to be the gain for the integrator. So really what this controller design comes down to, all this work was to find the 3 gains, Kp, Kd, Ki, for my exact same controller as we're going to see as I used in design 1, just the gains are flipped around. So really all I've done in the end is change what those 3 gains are, and it's going to change the behavior of my controller. It's still a PID, just with different gains on the P, the D, and the I component. And we're going to see at the end that for a PID controller, instead of going through this root-locus method, instead of going through selecting the desired closed-loop poles, there are alternate methods we can do that really jump to the heart of what the PID control is about, these 3 gains, and going directly and changing what these 3 gains are and seeing what the outcome is. But we'll talk about that after this example. Now I can go in and put in the gains I just found. And that's what I'm doing in this design too, saying Kp, Kd, and Ki. And we're going to be using that same controller, that same Simulink file we used before, because I made it robust so that it's taking those variables in from MATLAB. So that's all I'm changing are the 3 gains, but the rest of this is going to be exactly the same. So now I'm going to run this and see what the output looks like, what the input looks like when I use these 3 gains as opposed to the ones from design number 1 on 33, 34, 35. We see that, again, they've shifted. We don't necessarily have any good intuition at this moment about how's the behavior going to change with this these 3 different gains, how's the input going to be different, because we see that the gain for, let's see, Kp and Kd is lower than it was in design number 1, and Ki it's lower, but that doesn't necessarily translate to input effort having a lower peak or a lower average or a lower total. That's why we're going to run this simulation. So I'm going to run this and see what its behavior is. And as a note, I'm still going to use that same limiter as I did in design number 1 to be consistent, of plus or minus 20 being the maximum. Again, I'm selecting this arbitrarily. This would have to do more with your hardware, but it will change the behavior of the system, because without that limiter, it's going to behave more like the theoretical would, but it's going to require such a high peak input effort, it's not going to be ever practical to implement because of that initial kick from the derivative controller. So I'll stick with consistency for 20 and negative 20 for my saturation or my limiter here. I do want to note again that for this simulation, I am not necessarily using the defaults in Simulink. If we go into the options here and we go to our solver and open solver details, I am making the step size a little bit smaller than the default, I think is times 10 to the negative 3, and the tolerance and the relative and absolute tolerances also I'm using -4 here. If we turn it too low, it's going to take forever to run, but I do want a little bit more precision so I can see the differences between the 2 controllers I'm using. So when you're using Simulink, you might want to play with these if you're not getting the results you expect, or if you want a little bit more precision. So now I'll run this and see its behavior. All right, so this is what I get out from the simulation. My output voltage, again, I wanted a steady state value of 5 volts, and it does get there. We see that we have our peak, and we see the input voltage here. The peak is at 20, since that's what the limiter was. So it does initially get all the way up to that peak, but then goes very quickly back down to 0, and then kind of smooths out here. So we're going to look in the comparison, how do these look? And if we look at the numerical evaluation, we see that for this we have a max overshoot of 17%, if we round off a little bit, and a rise time of 0.692 seconds. Now we're going to compare design 1 and design 2. Before we do, we can, without doing the simulation in Simulink, we can get that closed loop transfer function, which is displayed here, and we see that we have two poles. They are close to the desired poles that we had, but we have those two zeros in this system as well. Note that the zeros of the closed loop transfer function are not the same as the zeros for the controller that we chose, because the closed loop transfer function is that GC/G0 over 1 plus GC/G0. So the zeros are going to change, but the poles are those that we desired or very close to them. Now, the behavior of this closed loop transfer function, we can't really well predict because we have two zeros and they're complex conjugates of each other, so it doesn't really match what we were looking at in Unit 2 when we were looking at a baseline second order system with an extra zero. The only thing we can note is that these zeros have a real part at -24, which is far from the closed loop pole real part at -1.15. But again, that rule of thumb doesn't hold true here, as we're going to see when we compare our two systems.